Okay, any questions before we start? If you remember, we were lastly discussing momentum conservation and collisions, and we will continue with momentum conservation and collisions today and make a review of also the potential energy. Now, any questions? Okay, then I have a question. Now, I have these two balls. One is a golf ball, the other one is a table tennis ball. Now, the golf ball is much heavier than the table tennis ball. Now, what I will do is I will just put them on top of each other and then release them. So they will just fall down, hit the ground, bounce back, and how high will the table tennis ball go after it bounces back? Let's say I release it from an H, the height H. Will it go bounce back up to height H? Ignore air resistance. What do you expect? Assuming air resistance will be small. Now, if I just bounce back one, the golf ball, how high will it bounce back, more or less? It will be more or less H, right? Yeah, it's H over 2. But of the order of H, it doesn't stop there, it doesn't go high up, it just stops, goes H over 2. The golf ball, that much? Much less than the table tennis ball? Yes. Let's see. It bounces more. Well, which one do you expect? Do you expect the air resistance to influence the golf ball more or the table tennis ball more? Or the same? Their shapes are almost identical. So which one will lose more energy? They must be. Okay, so let's see. Well, the golf ball jumps higher, so does that mean that it loses less energy? Yes or no? Yes, yes. No? Yes or no? Why yes, why no? Okay, definitely the golf ball jumps higher, but what does that mean? Does it mean that it loses more energy or less energy? Okay. Okay, so which means?
Which means when the golf ball impacts the ground, it will accelerate greater than.
No, so you are saying that the velocity of the golf ball after it bounces back is larger. Is that what you mean, basically? But what about the energy? This is the question. Which one loses more energy? This one loses more energy. Now, this is the example. I mean, I'm not making any I'm not telling you to make any assumptions. This is the example. I just drop both of them. This is how much they jump. Which one loses more energy? One came after the jump, one came to this height, the other one came to this height. This is the golf ball, this is the table tennis ball. This loses more. Why? Well, you have 50% of getting the right answer. So the thing is, why do you think that one or the other one loses more energy? The golf ball. This, okay. It's more rough, the surface.
Yes, because of friction, air friction is less affecting on the golf ball because of its
roughness.
roughness.
But nevertheless, this is a bit larger than the table tennis ball.
I know, but
Still.
that falls on the
Okay, so your friend is saying that it's the golf ball that loses less energy because the air resistance, the drag force, is smaller for the golf ball. That is what your friend claims.
I think they have the same, they lose same amount of energy, but the golf ball had bigger energy at the beginning. So
Why?
because its mass is bigger. So
Okay, this has your friend is saying this has a larger mass, so it starts with a larger energy. And since I'm assuming your claim is that the drag force is more or less the same, so they lose more or less the same amount of energy. But nevertheless, this goes higher up because fractional energy lost is smaller for the golf ball. So you see, the final height divided by the initial height is nothing but the fractional energy left. So since the golf ball has a larger mass, even a small change in the, you see, let's see, we drop it from the same height. This is how much the golf ball lost in height. This is how much the table tennis ball lost in height. If we multiply it with g times the mass, it should give me the amount of energy lost. Well, the height is smaller for the golf ball, but nevertheless the mass is heavier, so they would lose more or less the same energy. But I would say the golf ball loses even more energy. Because you see, if you compare the weights, be careful with your heads. No, compare the weights. You see, the difference in the weights is not just a factor of 2. The golf ball is much more heavier than the table tennis ball. So when you have this number, this height difference multiplied by the mass of the golf ball times g gives me how much the golf ball loses energy, compared with this height multiplied with the mass of the table tennis ball. So I would say the golf ball loses much more energy. So there are two factors that causes the golf ball to lose energy. One is the air drag, and maybe your friend is correct in the sense that it might be feeling less drag. But the collision, in the collision process, they also lose energy. So we don't know what is the coefficient, inelasticity coefficient of this collision. So probably in the collision, the golf ball loses most of its energy. But still, we can say that when the golf ball bounces back, it is velocity after colliding with the surface of with the ground is more or less equal to its velocity just before the collision, maybe just a factor of 20% less, but more or less of the same order of magnitude. Now let's come back to this example. I will just put them one on top of the other one and release them from a height h. What will happen after the collision? How high will the table tennis ball go? Just h, a bit less than h, a bit larger than h? It will be the same. Why? Well, unless it was larger, I wouldn't bring it as a demonstration. Okay, but why? Let's see. Let's first see it, and then we can discuss why does it happen. Now, what was the ratio? I mean, did it go twice as high, 3 times as high? Twice? Let's see. No. Okay, I was lucky the first time. So what is the fraction of the height? Was it twice? I mean, I think it went more than twice my height. Well, let's try it here. You see, the height difference was just this much. And after it bounced back, it was like middle of the screen. How high did it go?
3 times as
to here? Okay, that is, I would say, quite high, right? Not just two times. Before it was this much. After the collision, it was this much. Now, why? That is what we are interested in. How can we calculate how high, in the ideal conditions, how high could it go? Okay, you continue.
When you give it, we can calculate from momentum equation M1, V1, and it's
M1 V1 is equal to?
When we find the result of the transform, we can calculate the kinetic energy, and then we can turn the potential energy, and we can.
Well, you basically have the idea. So what we need to do is, when they are falling down, we should first calculate what is their collision their velocity before the collision, what will be their velocity after, and to do this we can use energy, for example, conservation of energy to calculate their velocity just before the collision. Then we can use the momentum conservation to calculate their energy right after the collision, and from that information we can determine how high the table tennis ball would go. Now let's apply that. Suppose we have these balls, the small one, the heavier one, we release them from a height h, and just before they collide, okay, we will be assuming that h is much, much larger than the size of the balls. So we can just use conservation of energy for any one of them, in fact. mgh, this is their initial mechanical energy. Finally, they only have the kinetic energy, 1 over 2 mv squared. So h is v squared over 2g, from which we can calculate. Well, either you can just go ahead and calculate the velocity from this equation just before their collision, their speed just before the collision, or just leave it as it is for the time being, because that will not be what we are interested in. Now let's see what happens. It is first the bottom ball that collides with the ground. So we have this golf ball, then we have this table tennis ball. They both have more or less the same velocities at the time of collisions. So one is moving downward with, this is the table tennis ball. The other one is, after it bounces back, it has the velocity of the goal, this velocity, let's say. Now, what will be the velocity? Both of them will be v. You see here, their velocity after falling a height h is independent of the mass. So both of the balls will have the same velocity just before collision, just before colliding with each other. After they collide, they bounce, the golf ball bounces back. Now, we are also assuming, just as a simplicity, to obtain the limiting value of the height, that the collision of the golf ball with the ground is almost elastic. There is no energy loss. But of course, we know that there is some energy loss. But we will just ignore it for the time being, just to get an idea of how high they would bounce. Now, we have these two balls. One is moving in one direction with a speed v. The other one is moving in the opposite direction with the speed v. Let's say this is the golf ball, this is the table tennis ball. Furthermore, we also know that the golf ball is much heavier than the table tennis ball. So we can just assume that the golf ball is infinitely heavy. just to get an idea. I mean, the thing that we are interested in will not be exactly how high it goes, but more or less. Should we expect it to go, I don't know, twice or 5 times or half the height? That's what we are trying to figure out, not the exact value. Now, what will be the velocity of the golf ball after, no, the table tennis ball after the collision? Infinite. Okay, may I conserve momentum if an object after the collision moves with infinite velocity? No. Okay, so it cannot be infinite.
Opposite direction of velocity, if collision
The collisions we will assume that they are elastic, so you are saying that its speed will be the same, but it will be just moving in the opposite direction. But let's see, if the speed is the same, then the height that it should go should be the same. No, I'm not asking for the golf ball. There's the golf ball, there's the table tennis ball, they move with the same speed in opposite directions, they collide. After the collision, what will be the speed of the table tennis ball? Okay, the golf ball, in fact, will just keep moving with the same speed. Its speed will not change because it's so heavy. Now, what is the speed of the golf ball, table tennis ball? Same as golf ball. Well, if it was the same, it would have jumped the same height. So that cannot be. Remember, initially this has a momentum in this direction, this has a momentum in the opposite direction. So if the only thing that changes is that this changes direction, still it will be difficult to conserve momentum.
The momentum of table tennis ball and plus momentum of golf ball over the mass of the table tennis ball after the collision.
So you are saying the momentum of the table tennis ball. Now let me put Vt over here. Plus the momentum of the golf ball
Over the mass of the table tennis ball.
the mass of the table tennis ball. Why?
Because of conservation of momentum.
Okay. This is the velocity of the golf ball after the collision, right? So since we are assuming that the mass of the table tennis ball is much smaller than the mass of the golf ball, so this will be more or less equal to mass of the golf ball divided by mass of the table tennis ball times velocity of the golf ball. Now this is the velocity of the table tennis ball after the collision. Right. Now let's see, does this make sense? Now you have measured their weight. What is the ratio, more or less? How heavy is this one compared to this one? What would you say? 10 times, okay. So let's say if it was 10 times, then this equation just tells me that the velocity of the table tennis ball after the collision is like 10 times its speed just before the collision, right? Now, if its speed is 10 times, then the height would have been 100 times. I would say that's too much. Okay, of course we are ignoring certain effects, we are making an approximate calculations, but the errors we introduce will just change the result by a factor of 2, let's say. So if you get 100 times the initial height, I would accept if in practice it just goes 50 times the initial height or 20 times the initial height. Now in the first example that worked, I just released it somewhere from here. It went quite high, but 100 times this height is something like 100 meters. That is the length of a football field. And this is not so high.
If we look at the frame of the golf ball,
Okay.
the tennis ball is coming toward us.
Okay.
We see after we bounce back from the table, we see that it's coming toward us with velocity and not necessarily 2 v. to it. And since it keeps us and bounces back, we see that it bounces back 2 weeks. But from your other reference frame, you will see that tennis balls velocity is more than that. 2v plus golf ball.
That is 3v. So if it is 3v, then what you are saying is then the final height would be just 9 times the first height. So do you think that makes sense? I mean, was it like 9 times the initial height that I released it from? More or less. I mean, 4 times is good enough. We are already ignoring many things. Was it 4 times as high? Or 9 times as high, more or less? Come on, I mean, I just released it from this height. So 4 times as high is 2. This is twice as high. This is 4 times as high. Now, it makes sense. It's 9 times. Let's go over your friend's argument. Now, we are looking at this from an initial reference frame. And in this reference frame, what we see is that initially there are these 2 balls. One is moving upward, the other one is moving downward with the same speeds, more or less. Then finally, when they collide, after the collision, what we observe will be this one. One is moving upward with the same speed, the other one will be moving upward with a larger speed. That is what our observation is. And all the velocities have, no, not all the velocities. Let's say this is moving down with a velocity v, this is moving up with a velocity v prime, v and v prime, they have more or less the equal speeds. And after the collision, let's say this is v double prime, this is v triple prime, v double prime is also more or less equal to v. The golf ball is so heavy that it's not influenced by this table tennis ball. Now let's go to a reference frame in which the golf ball is at rest. This is a different reference frame. Is this an inertial reference frame? So let's see, the golf ball just bounces back, but it is accelerating. That is the second question. When we were talking about the conservation of momentum, we were saying that momentum is conserved only if there are no external forces. Here we have a system with external forces. How can we say that the momentum is conserved? There's gravity, which is an external force. Okay. Okay. If momentum is conserved, which is true only if there are no external forces, and in this case, there are external forces. Well, gravity, there is the weight. Both of the masses have weight. No. The flight time?
Yes, the flight time.
The collision time? Okay.
And very short, that's why it doesn't affect.
Well, you see, the change in the momentum of a system is equal to force times delta t. So if delta t is very small, delta p is equal to 0, almost. So momentum, during the collision, momentum is conserved, more or less. Okay, so momentum conservation we can still use. Now, what about this inertial or non-inertial reference frame issue? Now, what we will be doing is, you see, we are looking at only during the collision, which lasts a very short amount of time. Just before the collision, the table tennis ball is moving upward with a velocity v. Now we are going to a reference frame which is moving relative to Earth at a constant velocity v upward. In this reference frame, this golf ball is at rest during the collision. It is moving upward with a constant speed v relative to Earth, which we assume is an inertial reference frame. So this new reference frame is an inertial reference frame. But of course, in this reference frame, the golf ball is not always at rest. Only during the collision it will be at rest because it has a constant velocity during the collision. So we can still go to a we can go to this reference frame in which the golf ball is at rest during collision. Let me also add that. Now this is an inertial reference frame. It is moving at constant velocity relative to another inertial reference frame, which is Earth. This reference frame is the reference frame which is moving upward with velocity v. In this reference frame, okay, we have this golf ball at rest. And then the table tennis ball, what is the velocity of the table tennis ball? In this new reference frame, in terms of these velocities, V triple prime? Definitely not. No, we are looking at the initial velocity, before the collision, just before the collision. This is before the collision, and then we will draw it just after the collision. This is before and after. Which where?
2v minus v double prime. Because the velocity
2v minus v double prime. Okay. So do you remember how we went from one reference frame to the other reference frame in terms of the velocities? Let's say this is what we had done. So we had one reference frame. This was the other reference frame. We just looked at a given point. Let's say this is R prime, and this is large R. So we said that, okay, small r, this is the position relative to one reference frame, is R prime plus large R. So if you just take the time derivative or look at how each one of these vector changes in a given time, you get V is equal to V prime plus V. To calculate the velocity in one reference frame in terms of the velocities in the other reference frame, you just add some velocities to everything. You add one velocity. So let's see. The golf ball initially has a velocity v prime pointing upward. To go to this reference frame in which the golf ball is at rest, we have to add minus v prime to the velocity of the golf ball. But then we add minus v prime to all the velocities to get to this reference frame. So if initially my table tennis ball has a velocity v pointing downward, finally it will have v minus v prime. This is just before the collision. Or you can also look at this one. What is the relative velocity between the golf ball and the table tennis ball over there? V minus v prime. That's the relative velocity. Relative velocities are independent of reference frames. The relative velocity here should be v minus v prime. Now, what happens to this table tennis ball in this reference frame? Well, this reference frame is simpler because one of the objects is at rest. And the object is at rest is very heavy. So during the collision, it will not move. So after the collision, what will be the velocity of this golf ball? Just imagine the table tennis ball. Just imagine that the table tennis ball just hits the wall. If it doesn't lose energy, what will be its speed right after the collision? The speed will be the same, it just bounces back. So it will just go up. The velocity will be just opposite, which is v prime minus v, or let me put it. It has the same speed, but opposite direction. Now, how did we go from this reference frame to this one? Add minus v prime to all velocities. This is how we went from this reference frame to the other one, in which the problem was easier to solve. Of course, we could have solved it in this reference frame. We already did. We had these lengthy equations from last week, but I mean, it will be difficult to remember them. You don't need to remember them anyway. So you can just go to another reference frame in which things are easy. This is the easy one. Then we can go back. Now, to go back, we just need to do the opposite of this transformation. Instead of adding minus v prime, we should subtract minus v prime or adding v prime. Just add v prime. Now let's see. This is the velocity of the table tennis ball right after the collision in the reference frame in which the golf ball is at rest during the collision. But that's not the reference frame we are making the observation. We are making the observations in this reference frame. So we have to go from this one back to this one. And how do we do that? Just add this v prime. Now if we add this v prime, we will see that this v triple prime is in fact twice v prime minus v. This is the velocity of the golf ball just after the collision. No, the table tennis ball right after the collision. Now its magnitude, you see v prime and v, they have the same speed. They correspond to the same speed, just in opposite directions. So this 2v prime is a vector pointing in that direction. Minus v is also a vector in the same direction. So these vectors are in fact, this vector is larger than this 2v prime. I have these three vectors all pointing in the same direction, all have this magnitude v. So if I just add all three of them, the magnitude is just 3v. So the final speed right after the collision of these two balls would be just 3v. And hence, it should go 9 times the original height. So this is not true. Since the height it will go is just proportional to the velocity squared, if the speed is tripled, the height just becomes 9 times. And, well, if you measure, probably you will get something like 7 or 8 times the initial height. This 9 is quite a reasonable explanation of our observations. Yes, questions? I'm expecting many of them from your faces. Your faces are already asking many questions. I want to hear them. Move? Okay.
Could we use a momentum change? For momentum change?
Which momentum change?
Could we use it
Sure. You see, if you remember last week, we had already studied these collision processes. Yes, this one. Here we use the conservation of momentum, conservation of energy. And this is what you would get. I mean, if you just put in the weights, the mass, and the velocity, you will get the same result. But it will be, I mean, just trying to remember all these formulas, I would say, is much harder than just making this switch back and forth between reference frames. Yes, questions?
Why did we change to other?
Which one? This one? Because I already know certain limits in collisions. I know that if I throw a light object to a heavy object, after the collision, if the energy is conserved, it's just the direction of the velocity changes. Speed doesn't change. That is something I already know. That is simple. So I want to use that information rather than writing down momentum conservation, energy conservation, etc. I just would like to study my problem in a reference frame in which the problem is simpler. That is a reference frame in which the golf ball is at rest. Because in that reference frame, this is so heavy that when the table tennis ball hits it, it will just bounce back with the same velocity, with the same speed. Just the direction of the velocity will be different. So that is the one simplification I wanted to use, rather than trying to remember all this one-line long formula.
How do you come to the conclusion that we just add V prime or subtract V prime?
What is the initial velocity of the golf ball in the initial reference frame? V prime. I want to go to a reference frame in which it is at rest. So what should I do to that V prime? Which velocity should I add?
V?
Now, the golf ball is moving with velocity V prime. Now, if I want to go to a reference frame in which it is at rest,
Always subtract V prime.
I have to add minus V prime so that its velocity in that new reference frame will be 0. Now, that is kind of a shortcut, I would say.
Why the principal doing upward velocity? Why principal velocity is upward? Because before the collision, both principal and ball were downward.
Okay, so let me just exaggerate it a bit, their separation. They are both falling down. Okay? They will be accelerating. And after the golf ball will hit first, and it will bounce back. So the golf ball is moving upward, the table tennis ball is moving downward. And then we have this collision. Questions? Well, one of you should volunteer. One of the three. Any questions?
Can I lead Brian?
This one. Now, you see, what I was trying to do here is, now, I have been always telling you that you choose your reference frame once and you don't change it. But here you are kind of told to use one reference frame. I would like to find how high it goes in this reference frame. But of course, this is not the simplest reference frame in which to study this problem. There is a simpler one in which at least one of the objects is at rest. So in that case, I have a single velocity to deal with rather than two different velocities. Now, I would like to go to this new reference frame in which the golf ball is at rest. In the initial reference frame, the golf ball is moving with a speed v prime. I have to determine the velocity of this new reference frame, this new one. That is the trick. Now, if we say that this is the, let's say, this is my initial reference frame. In this reference frame, O prime, the velocity of the golf ball is in the old reference frame, we said this is v prime. What I want is I want the velocity of the golf ball in the new reference frame to be 0. I know how they are related. Velocity of the golf ball in the O reference frame is equal to velocity of the golf ball in the O prime reference frame plus their relative velocities. Or velocity of the golf ball in the new reference frame is nothing but velocity of the golf ball minus v. This is what I know. I want this to be 0 because I'm going to a new reference frame in which the golf ball is at rest. But this tells me that this v, the relative velocity between reference frame, should be equal to the velocity of the golf ball. I should be moving with the golf ball. Now, if I am moving with the golf ball, remember in this equation, these primed just means the velocity in the new reference frame. V prime is equal to v plus minus v. So these velocities in the new reference frame are nothing but velocities in the old reference frame plus minus the velocity of the golf ball. This is how I go from this reference frame to this one. Now, any questions on this one? Clear? Or still sounds French? Now, once I agree that the only thing I need to do to go from this reference frame to the other one is that I should add minus v prime. This is the velocity of the golf ball. V prime is the velocity of the golf ball here. I should add minus v prime to all velocities. If you agree that this is the recipe to go to transform the velocities in one reference frame to the other one, then I do this transformation to everything. I have the velocity of the golf ball, which is v prime. I add minus v prime to that, so the velocity of the golf ball is 0 after in this new reference frame. That is what I wanted. Then there is the velocity of the table tennis ball, which was initially v. I add minus v prime, so now it is v minus v prime. So this is the velocity right after the collision, right before the collision in this new reference frame. Now this reference frame is easy, as I said, because the heavier object is at rest. So the only thing that happens to the lighter object is just it changes its direction of motion in an elastic collision. So it just changes its direction of motion, so the velocity just gets this minus sign. This is the same vector, this has the same speed, but pointing in the opposite direction due to this minus sign. So this is the velocity of the table tennis ball right after the collision in this new reference frame. Now, of course, we have to go back to the initial reference frame in which we are looking at. We are making the observation. And to go to the initial reference frame, I just do the opposite of this one. Instead of adding minus v prime, I just subtract minus v prime. That is adding v prime. So I go to this one. If I add v prime, the golf ball now moves upward with the same speed. V double prime is also v. And this one just becomes, this is v prime minus v in this one. If I add v prime, I get 2v prime minus v. This is 3 times the initial speed. Since the speed after the collision is 3 times, the height that it will go up after the collision will be 9 times. It's the square of the velocity. It's the square over here. So the height should be 9 times. And that is more or less what we observe. Questions? No questions? So then let's have a coffee break and see you after 10 minutes.